Welcome to section 4.1, Calculus. We're doing antiderivatives. And this is the introduction to antiderivatives. They're also known as integrals. And so, first of all, I want you to do a few warm-ups here. You can pause this, but I want you to graph a possible f of x given the f prime of x. Pause that, and then also try some of these things as rewrites, maybe using negative exponents in some of those. Now, I'm going to go ahead and graph this now. If I look at this as f prime, once again, I look at my zeros. My zeros tell me a lot. On each side of these zeros, my derivative is either positive or negative. Here it's negative. So if f prime of x is less than 0, that tells me that f is increasing. I'm sorry, decreasing. There we go. And then here, f prime in this interval, and I like to put these little slashy lines, in this interval f prime is greater than 0, so f would be increasing. And then so this is f decreasing and then f increasing again, because f prime is positive, f prime negative here. So if I want to do a sketch of this, and I know I'm going to have relative maxes and relative mins along the way, here I have f is going to be decreasing. So I'm going to go like this. I'm going to decrease and flatten off here. Then I'm going to, since f prime is positive, I'm going to increase, flatten off. And then I'm going to decrease again here. And I just want the general shape here. And I decrease quite a bit. And then I flatten off, and then I'm going to increase again. So that would be a possible f of x. Now, when you'd graph this, you possibly did it up here. So maybe we had one up here. So it's here. It's the same exact curve. It's just shifted up. That would be a possibility as well. I could do an infinite number of these up and down, and with those graphs, they tell me quite a bit if I'm given f prime and I want to find f. Now we're going to do the same thing, but we're going to do it with the expressions rather than a graph later on. Now rewrite these. You can go ahead and pause. If you don't know what I mean, then I'm going to use these in antidifferentiation, so I want to write them possibly like this. This one here, I'm going to do what I call the rabbit method. And this one actually is a rabbit with 3 ears. So I'm going to divide these. X squared divided by x to the 1/2 would be x to the 3/2. And I covered that up. I think it's a plus. And so we have plus 2x over square root of x would be 2x to the 1/2. And then minus 1 over square root of x would be x to the negative 1/2. I apologize if that's a minus. I can't tell in there now. This one, you FOIL this out. I found out that I'm not as good at FOIL as I used to be. And so we expand this. I'm just going to pause it. And we end up with this once we expand it. Smiley face, I call it, foiling out. Okay, then if we have this derivative, if we take the derivative of x to the 4th plus 2, this is 4x to the 3rd. This one, 4x to the 3rd. This one here, 4x to the 3rd. E is a constant. And so we just have a derivative of 0 there. So if we get 4x to the 3rd, 4x to the 3rd, 4x to the 3rd. So what if I ask you this question? If I know the derivative is 4x to the 3rd, what would y equal? Well, if you look at this situation, this situation, this situation, all these could be possible answers. So what we do is, to represent these constants, we use just that. Y would be equal to x to the 4th plus some constant. And we use that plus c. And that goes back up to my graph as well. I don't know how this stuff is going to be shifted up and down, so I can treat it with a plus c, and that would say, oh, this represents all the graphs. At some point in time, I might say, oh, I want to lock in the graph that passes through this point. And we will do that at some point in time. But right now, we just want to do a plus c. And so this leads us into antidifferentiation. And so what we want to do is take the derivatives and figure out how to go backwards. And so I'm going to do a bunch of derivatives on this side and then find the corresponding integrals over on this side. If we take the derivative and use the power rule, this is the power rule, I take the n out in front and I raise the exponent to 1 less power. That would be the derivative. So now I'm going the other way. So in order to do this, I have to account for some of these values and stuff. So what I'm going to do actually is I'm going to take the exponent and first of all raise it to the 1 higher power and then divide by that power. And don't forget now we have something that's called plus c. So this is x to the n plus 1 all over n plus 1 plus c. Now how can we check our answer? Well, we can always take the derivative of this to figure out if what we're doing is proper. So if I did take the derivative, that means take this out in front, which means these would cancel, and raise it to the 1 less power. I think you can see, hopefully you can see that that is equal to x to the n. Now I like a little bit of color. I don't know what I'm doing with this gray. So we'll get rid of this gray. Now if I take the derivative of 4x, we all know that that's 4. So if I go backwards here, if I see the antiderivative, oh, by the way, this is the integral symbol. That means take the antiderivative. So the antiderivative of 4, and we'll talk about this dx later, but it just kind of goes away for now. But this 4 antiderivative would be 4x and then plus c. So this is the integral symbol here. So the derivative of sine of x is cosine of x, and then the derivative of cosine of x is negative sine of x. Can you figure out what these might be? Why don't you pause this and think about that a little bit before you watch me do it. But now the integral of the sine of x. Well, I know the derivative is going to be positive cosine. So if I go backwards, this would be negative cosine of x plus c. Take the derivative of this and double check. If I take the derivative of cosine, it's negative sine, but I already have this negative. Well, yep, that works. Derivative of a constant goes away. So what's the antiderivative of the cosine? Well, I can use this straight right here, and this would be, to me, the sine of x plus c. Derivative of sine of x, cosine, done deal. How I try to memorize these things is that I just remember one thing. I remember that if I have sine of x, cosine of x, I memorize this one thing. And if I kind of continue this on, I know that the derivative of the cosine is negative sine, and I know that the derivative of negative sine would be negative cosine, and then the derivative of negative cosine would be positive sine again. It's a cyclical pattern of 4. So what I think is that when I take derivatives, I'm going down. When I do integrals, I go up. So when I take the antiderivative of the cosine, I know that it's going to be the sine. If I take the antiderivative of sine, since I know that this is the derivative, it can't be cosine going up. So it's got to be negative cosine, and that's borne out here. So like I said, I only memorize this, and this pretty much tells me everything I need to know. Okay? I can help you in class too if you didn't understand what I did there, but that's just a memory device. Let's go on to the next page. So we have the antiderivative of 2x now. When we look at this, some of you can just brain this and say, oh, x squared. If I take x squared, the derivative of x squared is 2x. That is correct. But let's now use these rules and see how this goes. If I have a constant multiple, it's just like taking the derivative. It goes along for the ride. So I'm going to write the 2 there, and then I'm going to take the antiderivative of x to the first power. If I do that, that means that I'm going to use this power rule here. I need to raise this to the 1 higher power, and then I'm going to divide by that power. And when I do this, obviously the 2's cancel, and I am left with that thing that you probably thought. I'm left with my x squared. Derivative of x squared is 2x. So you're in business. So that's how you use the power rule. What do I do with this one, number 2? Well, with this denominator here, I need to rewrite. So I did the rewrite. I haven't done anything else besides that. The 3 goes along for the ride. So I can write the 3. And then this is going to be x to the 1 higher power. Be careful. It's negative 3. That's 1 higher. And then divided by negative 3. Plus c. And then I'm going to simplify this. Remember, don't leave your answer with negative exponents. These cancel, so I'm left with negative 1 over x cubed plus c. If you're in doubt of this, take the derivative of this, double check that it goes back there. If I do this one over a sum, well, this is the same thing as what we had up here, except for it's twice as much. So I'm going to get 2x squared, and then you just do piece by piece, just like you do the derivatives. And so I do this piece, and then this one here, I already got the answer over here, so this would be negative 1 over x cubed plus c. So the purpose of this example is just to show you that you do it one term at a time. Integrate this, integrate this. So the integral of the sum is equal to the sum of the integrals. No problem. Here's a fractional exponent. Use the power rule again. Try this. Maybe pause this and go ahead and try it. Raise it to the one higher power, which would be the 5/3. X to the 5/3, all divided by 5/3. I should not use slanty fractions. That's one of my big rules. But I'm doing it right now. Now I just need to resolve this. Dividing by 5/3 is the same thing as multiplying by 3/5. So my overall answer here would be 3/5. And then my x to the 5/3 is in the numerator. And then plus c. There's my answer. So with this division, some of you can get this right away and you'll just start flipping this over. Some of you will have to rewrite, and that's fine, whatever works for you. And so this would just be 3/5 5x to the 5/3 plus c. Moving on. This is why we had those little warm-up problems for you, is because I need to simplify this here. There is no particular quotient rule that we have, or exacting quotient rule that we have for integrals. So I need to resolve this. So this was all plus sign. So x to the, I covered this stuff up. That's not very good. X to the 3/2 plus 2x to the 1/2 plus x to the negative 1/2. Now, in all actuality, and we haven't talked about this, but we will, I need to cover up that and multiply it by dx. So I'm going to do it term by term. This is going to be x to the 5/2 all over 5/2, which means that I do 2/5, plus x to the 3/2, the 2 goes along for the ride, one higher power. I divide by 3/2, which is multiplying by 2/3. So the 2 is already there, the first 2, and I'm going to have that 2/3 out front as well. So dividing by 3/2 becomes this 2/3. And then this one is to the one higher power, which would be x to the 1/2 divided by 1/2. I hope you can see that that's just 2. Clean this up a little bit. 2x to the 5/2. We're going to get a lot of fractions here. I learned how to do fractions by doing calculus. 4/3, so it's 4x to the 3/2 plus 2x to the 1/2 plus c. There's my integral. I highly recommend that you take each one of these terms, take the derivative of them to make sure that you get back to here, here, and here. And double check to make sure I didn't make a mistake. Next one. 2 goes along for the ride. So the antiderivative sign, well, let me think. The derivative of the sign is the cosine. So it can't be cosine, so it's got to be negative cosine. That's that little branching thing that I did earlier. So it's going to be negative 2 cosine of x plus c. How about this one? Woo! This one looks kind of nasty. Well, if you remember some things, what is the derivative of the tangent? Well, that's going to be equal to the secant squared of x, or the derivative of the secant of x. Well, that's the secant of x times the tangent of x. Well, that's what I have here. So what you can do is use some of our rules where we did have derivatives and work backwards. So if I do this one, the antiderivative secant tangent will just be secant. So this would be secant of, theta. Secant of theta, and then I got minus, so that would be minus tangent of theta. Don't forget your plus c. When I was in high school, I forgot plus c's on every one of my problems on a test. My teacher took a half off every time. So me being the vindictive person, well, I usually just take 1 point off and don't keep on penalizing you, but make sure you put the plus c. Now we can make our particle problems more interesting too. I can give you the velocity or the acceleration, and then we can find a possible position function. And then if we know something that's called an initial value, that's kind of like on the graph earlier. Like I said, if I know a point that's on the original curve, I can lock it in. I know what curve I'm talking about. And that's what I'm talking about here. So let's try these and see what happens. First of all, we need to put these in differential form. Differential form means that this dx is going to go over here with this term on the other side. So if I have dy, I'm going to cancel it here, and I'm going to cover this up and multiply it by dx. So it's going to be dy is equal to 4x to the third, 4x plus 3 dx, and that's now set up for my integral. These pieces mean small piece of x, small piece of y. So when I integrate both sides, somewhat like algebra, what you do to one side you have to do the other. When I integrate both sides, this is the antiderivative of 1. Well, normally we would say that that would be x. Derivative of x 1, yeah, okay. But this is with respect to y. So I'm going to get y. We'll talk more about that, but that's all you have to do with that piece. Then this piece, I know that this is going to be 4x squared over 2 plus 3. I don't have a variable there, so I need a variable there. And don't forget the plus c. This is called your general solution. General because I have the plus c. Now what they tell me though is they tell me some value on my curve that I can plug in now, and I can go ahead and find this c. So my y value is 6, my x value is 1. So to find the specific solution, I can plug these things in. 6 is equal to 4. Let me pause this for you. So I simplified 4 over 2 and got 2. Wherever I saw x, I'm going to plug in this 1. So it'd be 1 squared, and then plug in the 1 here. Now I can go ahead and find c. So c is equal to, oh, I'm stretching myself. I don't know if I can do that in my head. Throughout this 5. Oh, yeah, I can. c is equal to 1. So c plus 5 is equal to 6, so c is equal to 1. Now I want to find my specific solution. And my specific solution here is going to be y is equal to 2x squared plus 3x. Now I put in my c value. So that would be the 1. So this is the solution that I want. Okay? This function where I found c is, I was calling it specific solution, but really it's called the particular solution. So the general solution is with plus c. The particular solution is when you find the constant value and you write it at the end. So let's try this next one. We set it up like we did the other one. dx, now this is dx dt. A little bit different than dy dx, but we can deal with it. I'm going to do the same thing. I'm going to take this dt and I'm going to multiply it by the other side. So if I have 3 sine of t minus 5, I cover this up and I'm going to multiply it by dt. So when I integrate both sides, you say there's nothing here. I say there is something there. What's the antiderivative of 1? So I get x, and this is x of t. So this is a position function. The antiderivative is sine. Remember, the derivative of sine is cosine, so the antiderivative would be negative. Negative 3 cosine t minus 5t. There's your antiderivative. And then if we go, oh, what did we forget? Oh, minus a half. Don't forget plus c. That is a huge, huge mistake. On the AP exam, you lock yourself out of many points if you do that. So now I can find my particular solution because they give me an initial value. So I can say that x of 0 is equal to 4, so 4 is equal to negative 3 cosine of 0 minus 5 times 0 plus c. This one, a lot of times you plug in 0, you're going to get 0 for all these values, but in this case you don't, because the cosine of 0 is 1. So be very careful. So this would be negative 3, that one goes away, plus c, so c is equal to 7. So first of all, this is my general solution. And then I want my particular solution. So I can write this as x of t is equal to negative 3. Had some technical difficulties there, but this is the final solution. I didn't write out my particular solution with 7 in there, but you just put 7 in there. But I want to find x of 2, and this is the best I can do without using a calculator. So you can plug that into the calculator to find out what that value is. So what did we do? We took the antiderivative, both sides, and I had the dx and dt on opposite sides, and then I solved for x of t, and then I went and found my particular solution. Then I could plug in the 2 and found out what x of 2 is. All right, thank you very much. I hope you enjoyed this. Take care.